Hello everyone, this is Jade with a cool and interesting physics problem to solve. Okay, so this physics problem is asking us how many billion suns are equal to the Milky Way, meaning how many billion suns is equal to the mass of the Milky Way. So before we get started in solving the problem, let's go ahead and figure out our knowns, or the things that we know, the values we know, and write them down. Okay, so let's start writing down what we know. So we know that the sun orbits at the center of the Milky Way, and it's about 27,000 light years away. So let me draw it like this. And so this is about 27,000 light years away. So it's orbiting at the center with a radius of 27,000 light years. And so we know the radius. So our radius, we'll denote that with r, is equal to 27,000 light years, like that. We also know that it has a period of 240 million years. So we'll use t for our period, and that period is 240 million years, like that. Okay. We also know some constants. So we know the speed of light. So the speed of light is 3 times 10 to the 8 meters per second. So that's the speed of light. And we also know that our gravitational constant with a capital G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram. Okay, and we also know the mass of the sun. So I'll use m sub sun to denote the mass of the sun. And that is 1.99, roughly 10 to the 30th power kilograms. Okay, so these are all the things that we know. Now, for the mass of the sun, m, and for the attracting mass of the galaxy, nm, where n is the number of solar masses, we can write this. And so we can write this. Instead of writing the mass of the Milky Way, we'll write it in terms of the sun. So that'll give us what we want to solve for, and it'll also eliminate our unknowns here. So we have our gravitational constant like before, being multiplied our mass by our mass 1, which we'll write in terms of n and the mass of the sun like this, and also being multiplied by the mass of the sun, and divided by our radius squared. And so this is what we'll use to solve our problem. Well, what else do we know? Well, we are solving for force here, and we know another way to write force. Another way to write force is mass times acceleration, our good old mass times acceleration. So we know that this formula is simply equal to mass times acceleration. But we don't know acceleration, so we're going to need to replace that in terms of something else that we do know. Well, we can write acceleration in terms of our radius and angular frequency. So I'll rewrite this as mass times our radius multiplied by angular frequency denoted by omega squared. So that's how we can rewrite acceleration. Okay, so now there's another problem. We don't know angular frequency. So we're going to have to do another rewriting in terms of something that we possibly do know. So we can write angular frequency in terms of our period. So we can say radius times 2 pi over t. And of course, that is squared. Okay, so now we have an equation which we can solve for n. Okay, so let's rewrite this a little bit more clearly. Okay, so we have our gravitational constant times m, mass of the sun, and I can go ahead and say squared because we're just multiplying by two of those over our radius squared. And that is equal to the radius times 2 pi over t squared. Okay, so this is our equation that we need to solve for n here. So let's go ahead and do that. Okay, so I'll start by multiplying the radius squared by both sides. Squared. And so I'll be left with gravitational constant times n squared sun. Oh, it's not going to be down there. All right, and then I multiply that by both sides, so we'll have r cubed here. All right, so let's isolate our n here finally. We'll divide by our gravitational constant, and I'm going to go ahead and divide by the mass of the sun squared as well, and then put it on this side. Oops, that's not too subscripting, so I'm going to just drag that up, maybe. Okay. All right, so let's rewrite our equation once more. So we have n, which is the number of our solar masses, and then we'll say r cubed squared sun. Okay, and I'm actually going to do one more step to make this look just a little bit nicer. So I'm just going to rewrite it like this. Mass squared sun. And I'll write this. Okay, alright, so that looks great. Now we can go ahead and substitute the known values that we have. Alright, great. So we know everything here. So let's go ahead and replace 27,000 here. That's 27,000 cubed. Our gravitational constant here, which we know is 6.67 times 10 to the negative 11. And let's have good habits here. We'll go ahead and write our units. And this one's kind of hefty one, so I'll write Newton meter squared per kilogram like that. And that's being multiplied by the mass of the sun, which is 1.99 times 10 to the 30th kilograms. Okay, things are getting a little bit jumbled here. Let's continue. Alright, and this is squared, gotta remember that. And also we have 2 pi over our period, which is 240 million, which I just used the m for, years. Okay, and that is also squared. Okay, let's now expand things out so that we can get the full picture and cancel out some things. Okay, so 27,000 cubes. So this is in light years. So we have light and we have years. So we want to get light in terms of speed and then in years in terms of seconds, or light in terms of meters per second. Okay, so we have 27,000 cubed. I'll write them separately because everything is getting cubed. So I should probably rewrite this way. And then we have light. The speed of light is 3 times 10 to the 8th power, so that's cubed. And then we have years. So we need that in terms of seconds because that's going to be our unit here. And years, a year in terms of seconds is going to be roughly 3.2 times 10 to the 7th power. And that's going to be cubed as well. All right. And let's go ahead and bring our, what we're multiplying here. So we're multiplying our 2 pi over our period here, and this is going to be our angular frequency. And let's go ahead and simplify this. So this will be 4, so this whole thing is being squared, so this will be 4 pi, we're looking at this here, so this is going to be 4 pi squared in the numerator, and then we're going to draw our huge vinculum here, and then we'll get to looking at our denominator. So our units, we're going to keep these units the same, because in terms of newtons and meters and kilograms, so that's already great. And that is newton. Let's go ahead and zoom in a little bit. Meters squared. All right. And then we have this being multiplied by a mass in kilograms, so that's already great. And this is squared. Okay, so let's draw it like this. And then let's take a look at, this is squared. Okay, great. Oh, no, we already squared it. Okay, great. And so we have our period here, and we're going to go ahead and write this in um, seconds as well. Sorry. So this is 240 million. So let's go ahead and expand that out. Instead of just using the m, we're going to expand that out into scientific-ish form. And then that is also squared. And that is in years. So now we're going to convert that to seconds. So it's 3.2 times 10 to the 7th. And that is squared as well. Super long, and it's kind of easy to get lost here. So let's go ahead and cancel things out. So we have converted our years to seconds. So we have that here and we have that here as well. And so since we know that, we can go ahead and cancel those out. So this will cancel out, that'll cancel out, and we'll only have 1 in the numerator. And so what I'm going to do is copy this, put this down here, and then since that's canceled out, we'll just have our 3 cancels with our 2 in the denominator, so it just leaves 1. And we'll get rid of that. And this looks great. And if we were to go through and examine, we'd see that all of our units cancel out here. And that's great. So that leaves us with a unitless number, which is what we want because we're looking for how many suns would fit into, or how many suns would make up the Milky Way. And so a unitless number makes sense because it's just a number of suns. And so if we go through and simplify this, we get 8.698 times 10 to the 10th power. And that is approximately equal to 90 billion. So we see that 90 billion suns is equal to the mass of the Milky Way. Thank you.